Okay, this is the second presentation on performing calculations in Java. And the first thing that we're going to look at before we do any calculations is look at the idea of constants, constant variables. And if we look back on the vending machine class that we created last time, there were some values that were unchanged, they were fixed. So as an example, the cost of a packet of crisps to the owner of the machine was 10 pence. The cost of a chocolate bar to the machine owner was 15 pence. The number of packets of crisps or chocolate bars in a single box was 10. And there was a markup value, which was the multiplication factor when we sold a bar of chocolate or a packet of crisps to someone buying out the machine, and it was a markup of 2. We bought for 10, we sold for 20. We bought for 15, we sold for 30. Now those values we used in calculations. We used 10, 15 for the prices and 10 for the number of packets of crisps and chocolate bars in a box. But we can use these things called constant variables, and it allows us to use a standard value for each of these, and we can just replace it with a name rather than using a value, which is sometimes a bit obscure, especially if your calculations are complex. So what we do is we declare constants at the top of a class, and we sort of do it in a slightly different place to our variables. So we separate our constants from our instance variables. Now there is a template called CSE 101 empty, which is installed as part of the BlueJ installation at college. If you want the template for your own use at home, then I can give you a copy of it on the VLE, and I'll have to show you where you need to install it. But with constants, we declare them almost exactly the same as normal instance variables. There's just a slight change in that we add the word final at the beginning of them to indicate that it can't be altered during the program's running. So the 4 integer constants that we're going to use in the vending machine class have got some declaration elements or examples at the bottom here. So whereas we would declare an integer variable crisp cost and assign it a value of 20, we're going to use the naming convention to use uppercase names for all our variables, and we use the word final at the beginning of the declaration so that we know or tell Java that these are constants, and anyone who's using the program or editing the program in the future will know that they're actually editing a constant. How do we use them? Well, we just use them in place of values. In the old vending machine class program, for example for fill crisps, where we said we added 10 to the number of packets of crisps in the machine, where we use num crisps equals num crisps plus 10, we would replace it with a constant which we would declare called box size. So we would say num crisps equals num crisps plus box size, which we would have declared as a value of 10. The same would apply for when we're declaring profit or calculating profit. When we're changing the value of profit, when we fill or put 10 packets of crisps in a machine, we would remove 200 pence or £2 from the profit because it's 10 lots of 20 pence. Instead of doing that, what we would do in this example is we would multiply a constant of box size, which is 10, by a constant crisp cost, which is 20, multiply those together, and then we would take them away from the profit in the same way. Benefit of it is that if all of a sudden the number of crisps in a box changes from 10 to 15, then we just change the constant. We don't have to go all the way through the program in order to make those changes. It's also the case if the cost of a single packet of crisps changes to 25 pence, we just change one constant and that would cascade through the rest of the program. We don't have to go through our program and make lots of changes, we just need to make one. So have a quick go at this, another pause the video moment. There's the original buy crisps code, and as it stands, we would buy a packet of crisps, we would knock one off the machine, and then we would alter the profit by the factor of 2 multiplied by the cost of a single packet of crisps. Pause the video and have a go at rewriting that code, only using the values of crisp cost, which is a constant set to 20, and markup, which is a constant set to 2. Pause the video, have a quick go at that and see what you get. And we'll have a look at the next instalment of our vending machine class. Okay, so we've got our vending machine 3 class downloaded from the VLE, loaded it up into BlueJ. So let's have a quick look at the code first. And let's just look at some of the slight differences that we've got. First of all, we're using the CSC 101 template, and we've got a section proportioned off that's separate from instance variables that deals with our constants. So we've got 4, one for a single packet of crisp, one for a single bar of chocolate, one for how many are in a box, and one for the price markup that we use to multiply up. We've still got our num crisps, num chocolate bars and profit instance variables, and those get initialized in the vending machine. The only inherent difference with this particular example and the previous one is where we've seen an opportunity to use a constant, we've replaced those values in the methods. So with our fill crisps, we've replaced the value of 10 with the constant box size, and we've taken the profit away by calculating the number of packets of crisps by the cost at which the cost of a single packet. In this case it's 10 multiplied by crisp cost, which is 15, so that means we take 150 pence away from the profit. In a similar way, we've done that with chocolate bars. We add a box of 10 chocolate bars by adding it on to num chocolate bars, and again we've worked out the cost of filling the machine with 10 chocolate bars, which will be 10 for the size of a box multiplied by the cost of a single bar of chocolate, which is 15. So 10 by 15 is 150, and we knock that value off the profit. The 2 buy methods for buy crisps, buy chocolate bar work in a similar way. We knock 1 off the value of crisps, and we knock 1 off the value of chocolate bars, and then we add the value of the money made onto the machine's profit. So that's the cost of a packet of crisps, which is the constant 20 multiplied by its markup of 2. So 2 by 20 is 40, so we add 40 on to the profit. Same with the chocolate bar, apart from the fact that a chocolate bar costs us 15 with a markup of 2, so 15 by 2 is 30, and we add 30 on to our profit. The view quantities and view profit methods are exactly the same. They just show us how many packets of crisps and how many chocolate bars are in the machine for view quantities, and for view profit it gives us a value of how much profit the machine has made. So if we were to demo this quickly, it should work in exactly the same way. If we inspect our machine, and as you'll notice straight away, we have a lot more elements in our object inspector. Okay, those won't alter because they're constant, so we just need to still keep an eye on our num crisps, num chocolate bars, and our end profit. So the first thing we're going to do, fill it with chocolate bars for 10, means our profit is 150 down, 10 by 15. Fill it with crisps, that's 10 by 20, that's 200, so 200 minus 200 minus 150 is minus 350. If I buy a chocolate bar, one goes down, value goes up by 2 times 15, which is 30. If I buy a packet of crisps, that goes down by 2 to a factor of 20, which is 40 less. So functionality is exactly the same, but we're now utilising constants in order to keep track of our values much more closely. Okay, so what we're going to do now is we're going to extend the program for vending machine a little bit, and we're going to include more functionality to deal with calculating the value of the company. When you work out the value of a company, it's the money that you've physically got hold of plus the company's assets. Now, assets tend to be anything that's generally tangible that can be sold off. With our company, the only sort of assets that we have that we can sell will generally be the value of our remaining stock. So the value of the company will be how much money the company has, as well as the value of the stock that's in the machine at its original purchase price. So we're going to extend that class to calculate the value of our company. So what we've got to our original vending machine class diagram is a new method called view co-value, and what we're going to do is we're going to use that to output the company value. So what we'll need to do is take the value of the profit in the machine, take the value of the number of packets of crisps in the machine multiplied by the cost at which we bought them, not the cost at which we sell them because they're actually unsold, and the number of chocolate bars in the machine multiplied by the cost at which we bought the chocolate bars. So what we'd have to do is perform those three calculations, and again, you can pause the video and have a look at this and have a go at it. What would the user.message statement look like to perform that calculation and output the result? Okay. Just going to have a little look at this concept of local variables. Now, if we were to just go out and perform this calculation, it can be a little bit messy. It's three lots of things to calculate, three lots of things to put together, add together, and then our user.message to output all these values, and we'd have to stick them all together with concatenation symbol. So what we can do is we can use something called a local variable, which is a variable that lives and dies within the method. It's not declared at the top of the class like other methods that we've used. It's actually declared inside the method, and we use it for basically temporary calculations when we run the method. We don't need the value of a local variable once the method is finished. We're perfectly happy to let the variable die or be erased from our memory. So we can use a local variable in the same way as any other standard variable. It gets a data type, it gets a name, we declare it at the top of a method where it's used, and it can only be used in that method. In fact, all the other methods won't even know it's there, because by the time the method has been finished, it gets deleted. If the only way that we can get that variable back will be to call that method again. But when that method stops running, that local variable dies. So it's only used as a bit of a local temporary piece of storage. And certainly the value that's in it doesn't get remembered either. So we've got a local variable, or we're going to put a local variable in there called co-value, and that's going to be used to temporarily store the value of the company and output the value in our user message class. We can give it a name without the preceding M, so we don't get it confused with a variable that's declared at the top of the class. We don't need to follow that very hard rule that we've sort of established ourselves, in that variables at the top of the class have an M to define them as a member variable. But local variables, because they don't effectively live as long as the program's running, we can just use our own sort of naming convention for a local variable. In this case, we're going to use an integer variable called co-value, and we're going to declare it locally in our method. There's exactly how it's going to work. Here's our method, view co-value, and we've declared the local variable as an integer called co-value. The company value is the amount of money in the machine. We add on the value of crisps in the machine multiplied by the cost it cost us to buy them, and we also add on the multiply of the number of chocolate bars in the machine multiply the cost of a chocolate bar at cost price as well. So we add on the profit, the value of the crisps in the machine, plus the value of the chocolate bars in the machine. Then we have a user.message box which outputs the value of company value in a sentence, so we see how much our company is actually worth. And we'll have a little look at that now. Okay, so I've opened up the vending machine 4 class. We've downloaded it from the VLE. It's compiled, and we'll have a quick look at it in the editor, but there aren't that much in the way of differences between vending machine 4 and vending machine 3. The only real difference is that all the way at the bottom we've added the view co-value method, and that incorporates the declaration of local variable co-value, and that's used to evaluate the value of the profit plus the value of the crisp in the machine added on to the value of chocolate bars in the machine. Add the 3 together, put that into co-value, and then use a user.message command to output that value. So we'll create an instance of a vending machine and inspect it, and again very quickly we'll fill it with chocolate bars, fill it with crisps, and as you can see in the object inspector there is no entry for that local variable. That local variable doesn't actually exist, and it will only exist when I run the view company value method. Even then it won't appear in the object inspector, but as you can see at this point, if I open up the company value method, it should tell us that the company has a value of 0, and it should. At the minute we've got we're running into debt with the amount of money that's in the machine, and 10 lots of 20 pence, which is 200, and 10 lots of 15 pence, which is 150. So 350 plus minus 350 is 0. Obviously, if we make a couple of purchases, and we buy a couple of chocolate bars and then buy a packet of crisps, that has an effect on the company value, and we slowly start making some money and the company has some value. Okay, so what we're going to do is look at another example of how we can apply calculations, and we're going to go back to the window cleaner example, and we're going to add more functionality to that, in that what we're going to do is start to add a charge to our window cleaning services, and we're going to present a final bill to the person who has the windows cleaned. So first thing we're going to have to think about is, do we need any new instance variables, and do we need any new methods that need adding to this existing UML diagram, and of the methods that already exist, do we need to make any alterations to them to accommodate our new functionality? So again, a couple of minutes, pause the video and see if you can come up with a new UML diagram. Okay, I came up with something like this. Basically, we need to be able to store the charge for cleaning the windows. We will need to have a new method which will present the total charge for that particular house or building that's having its windows cleaned, but we'll also have to change the wipe window method to incorporate adding on a value to total charge every time we clean a window. So let's have a look at our method of cleaning, or costing the cleaning of a window, and it's all going to be based on a basic charge and the height of the window. So the higher up you go, the more you pay. Danger money, in fact. So the basic cost of cleaning a window is 10p. So it doesn't matter whether you're on the ground floor or the top floor. But we're going to have an additional height charge of 2p per floor. So if we're on floor 6, we will charge someone 10 pence, which will be the basic cost of cleaning a window, and then 2 pence for every floor that we are above the ground. So in this case, on floor 6, it's 2 lots of 6p, which is 12p, plus the basic cost. That'll cost us 22p for cleaning a window, or one window, on floor 6. In order to accommodate that, we're going to have two new constants, one called base charge, which is our basic cost of 10p, and something called floor factor, which will be our multiplier for multiplying out the cost of cleaning it the higher up the building we go. So what that means for us is that we're going to have to change the wipe window method in order to accommodate that calculation. It's quite complicated, not too complicated, but we have to use a local variable inside wipe window in order to accommodate the calculation. So what we do is we use our integer charge for local variable, and that is worked out as our base charge, which is our 10p, and then we add on to the base charge the value of the current floor that we're on, multiplied by the floor factor, which is our 2p multiplier. We then get that charge, and then we add the value of charge onto the total charge. So that will then be done for every window in the property. We'll also have to change the bill and reset method, because what we'll do is output the value of total charge that's presented to the owner of the building for whose windows we've just cleaned, and then once we've presented them with the bill, we can then reset total charge to 0, and then we're ready to move on to another building and clean the windows in that one as well. So let's have a look at that one. Okay, so I've got the Window Cleaner 2 program downloaded from the VLE. I've got it open, and let's just have a look at the code in the editor first. And there are one or two changes, not too many, but let's have a look at where we're going. First of all, we've got two constants which we've declared. One for the base charge of 10p, and the other one for the multiplier flow factor, which is that 2p per flow multiplier. We've got two instance variables for current flow and total charge, and we initialize those to 0 in the constructor. If we call go up, we just add one onto the current flow, that doesn't change. If we go down, we take one away from the current flow, that doesn't change either. The new charging system kicks in when we wipe a window. If we wipe a window, we need a temporary local variable to accommodate it. We tell the user that we're wiping the window on that particular floor. We then calculate the charge based on the base charge of 10p. We multiply the current flow that we're on by the flow factor, put it into charge, and then add that value of charge onto total charge. And every time we wipe a window in that building, that will automatically get added on. We'll see that when we do an object inspection, when we have a look at the running program. When we call bill and reset, we output the total charge to the customer and reset total charge to 0 for the next building. So let's have a go. Create an instance of a window cleaner, and we'll inspect the variables. Again, now we've got constants in there, we'll get to see those, but obviously they won't change. So let's imagine where we are. Let's just say we're doing a 2 up, 2 down, and we're going to clean the 2 windows on the ground floor. So let's clean the first window, and it tells us that it's wiping window on floor 0. Now, if you take into account what we've done, it'll be 10 pence plus 0 times 2 pence. So that'll just be a 10 pence added onto our total charge. Let's wipe the other downstairs window. And again, it tells us we're wiping the window on floor 0. Same again. Flow factor is 10 pence base charge plus 0 times 2p, which is 0. So it should only be another 10p added onto our total charge. Let's go and get in the cradle. Go up one level, so we go up to floor 1. As you can see, we're on current floor 1, and there's 2 windows on this floor, so let's wipe the window. That means we're wiping the window on floor 1. That'll be 10 pence plus 1 for floor 1 multiplied by 2p, so that should be another 12 pence. Takes it to 32. And if we wipe another window on the same floor, again, that'll be 10 pence base charge plus 1 multiplied by 2, which is 2, so 10 plus 2 is 12, and that's another 12p. Let's say we've cleaned all the windows. We go down to the ground floor and bill and reset, so we can charge this particular person 44p, and once they've paid, we reset total charge to 0, and we can move on to the next property. Close down the object inspector, remove that object, and then we can close the project. Okay, to summarise, we initially looked at the use of constants. They're used to store values where we don't want them to change, and we use the word final to basically declare a constant and give it a value. Useful because we don't need to remember the values. We can just refer to them by name. The other useful thing is that if we do need to change the value of a constant, we only need to change it in one place, and that value cascades through the rest of the program. We've also looked at local variables, which are used as temporary variables for things like calculations, and they will only live for as long as the method is being run in which they've been declared. The temporary storage, once the method is completed and stops running, then that local variable will be wiped from the memory as well.